Good morning, dear. Good evening, sorry. Good evening, dear students. I hope you are all well and safe. We will continue now with the probability 2, and we'll start lecture 13, which is about joint discrete probability distributions. I hope you read the previous two lectures, 11 and 12. They are on YouTube. And I am sorry about the delay of lecture 1. I sent it a long time ago, but I don't know what was wrong with this lecture. But anyway, study them. And if you have any questions, feel free to email me. I will be happy to answer any questions. Okay. Lecture 11 was about continuous distributions, specifically beta distribution and Cauchy distributions. Okay. And then lecture 12, we started the topic of joint probability distributions. And I explained to you in that lecture what do you mean by joint probability distributions. This is if we define more than one random variable on a given sample space. And I gave you two examples, one about tossing two dice, and we do care about the number of dots appearing on die 1, and at the same time the number of dots appearing on die 2. So if we call the first the random variable x and the second the random variable y, okay, I mean the outcomes on die 1 and die 2. And if we want to study these two random variables, say x and y jointly, this is what we mean by joint probability or joint random variables or joint probability distributions. Okay, last time in lecture 12, we defined what do we mean by joint probability distributions, and we said we can define 2, 3, or any number of random variables, and we studied the joint behavior of all of them. But we said for simplicity, we are going to start with the case of 2 random variables. And then after we understand all details, in this case, we are going to extend it to more than 2 random variables. Also, we are going to cover both the discrete case and the continuous case. We started last time with the bivariate case, and we defined the joint cumulative distribution function, capital F, X, and Y. I gave you the definition and the properties which are extension for the CDF and its properties in the univariate case, which you all know. Okay, and I gave you the definition before we start talking about discrete or continuous, because the definition and the properties are the same for discrete and continuous. The calculation differs, because if you want to get the CDF for discrete, you are going to use summation. If you get it for continuous, you will use integrals. That's the only difference. But the definition is the same. The properties are the same. And then also, we've talked about what we call the marginal CDF, which means if you know the joint CDF for X and Y, how can you get the CDF for one of them? I mean X or Y. We call it marginal. Okay? And after that, we started to talk about discrete probability distributions. We defined what do we mean by joint discrete random variables, and then we defined the joint probability mass function, which is an extension for the probability mass function in the univariate case. which is just a probability. Remember, in the univariate case, f of x is what? A probability that x equals x. Here we have x and y, so it will be a probability that x equals little x and the variable y equals little y. Okay, and then the properties of the probability mass function, which is again an extension for the properties of the probability mass function in the univariate case. The first property is what? That the function has to be non-negative for all values. In the univariate case, we say for all values of x in its domain. Here it will be for all pairs, x and y in their domain. Okay, and then after we defined the joint probability mass function, we moved to what we call marginal probability mass function, which is the function for one of the variables. So if you know the joint probability mass function for x and y, how can you get the probability mass function of x alone or the probability mass function of y alone? Okay, now we are going to continue with this subject, the joint discrete probability distributions. Okay, I hope if you have any questions, please feel free to ask me. Okay, now the next slide, the first few lines before the title conditional probability mass function, I mean this part, this is included in lecture 12. Okay, now we start this topic, the conditional probability mass function. What's the definition of the conditional probability mass function? It says let x and y be jointly discrete random variables with the joint probability mass function f of x, y, and the marginal probability mass functions fx and f of y respectively. Okay, so that's what's given. So what's given? That we have two random variables which are jointly discrete, and we know its joint probability mass function, and we know their marginal probability mass functions. What do we want now? Then the conditional probability mass function of x given y equals y is. So that means here we do care about the behavior of the probability mass function of x if you fix the random variable y at a specific value, we call it little y. Okay, so here you are fixing a capital Y at one of its values. Okay, and you want to study the behavior of the other variable, which is in this case x. Okay, so what's the definition? We denote it by f of x given y. This is the notation. Okay, what's that? This is a ratio of two functions. The one above is the joint probability mass function of x and y, and the one down here is the marginal of y. So that means the conditional is what? The joint probability mass function of x and y divided by the marginal of the random variable you are conditioning on. Here we are conditioning on y, so you divide by f of y. As you know, if you write any probability mass function or f density function, you have to attach the domain. The variable here is x. So what are all possible values of x? Here we say x belongs to Rx. By Rx we mean the space of the random variable x, or the domain of the random variable x. Since you are dividing, for this ratio to be valid, the denominator shouldn't be 0, right? But in fact, we know that this is a probability mass function, and any probability mass function is non-negative. Okay, so that means all you need to assume that it is positive, greater than 0. Okay, now if we, in a similar way, if we want to get the conditional probability mass function of y, if we fix x this time, So what will be the notation? The notation will be f of y given x. Okay, what's that? It is again the joint probability mass function of x and y divided by the marginal of the random variable you are conditioning on, which is what in this case x. So it is f of x. Okay, again you attach the domain, y belongs to ry, and you assume that the denominator is greater than 0. So this is the definition of the conditional probability mass function. Now we have some remarks we need to mention. Number 1, if we take this conditional probability mass function and we write its definition, the joint divided by the marginal, okay, we are talking about the discrete case, right? So what's the probability mass function in the discrete case? It's a probability. From last time, this function is the probability that x equals little x and y equals little y. Okay, what's the denominator? This marginal probability mass function. Again, it is a probability. So it is the probability that y equals y. Okay, now when you divide this by this probability, this is a joint probability, divided by this probability. Do you remember what's this? From probability 1, the course probability 1, it is the conditional probability that x equals x given y equals y. So what do we deduce from this remark? That the probability mass function conditional. The conditional probability mass function is just the conditional probability. Okay, and remember, the marginal probability mass function is just what? A probability. The joint probability mass function is what? A probability. So can you see? In the discrete case, any probability mass function, whether it is joint, marginal, or conditional, it is what? The corresponding probability. Okay, the second remark. We say that f of x given y is a probability mass function. So that means it possesses the properties of a probability mass function. What's the properties of a probability mass function? 2 properties. The first one, the function has to be non-negative, right? And this is true. Why this is true? Because if you go to the definition of the conditional probability mass function, it is the joint divided by the marginal. The joint is non-negative, right? And the marginal is non-negative. So that, in fact, the denominator f of y is positive. Remember the condition? F of y is greater than 0. So that means this ratio is non-negative. Okay? Now the second property. What's the second property for any probability distribution or any probability mass function? That's the sum. If you add over all values of the variable, then the sum has to be what? 1. Let us see if this is satisfied in our case. What is the definition of this conditional probability mass function? It is the joint divided by the marginal. Remember the definition? Now, this denominator is a function in y, but you are adding over what? Over x, right? So that means this is constant with respect to the summation. So take it outside, take it here. So it becomes what? 1 over fy summation f of xy, right? Now, what do you get when you add the joint over x? From last time, this is the marginal of y, right? The marginal of y, which is what? F of y. So now you have f of y divided by f of y, so the answer is 1. So that means the properties of the probability mass function holds here. Okay, the following remark, number 3, about calculating probabilities conditionally. So if we want to get the probability that x lies between a and b, given that y equals y, how do we calculate it? Okay, if you forget about the condition, what's the probability that x lies between a and b? Remember this from the univariate case. It is the sum over values of x from a to b, and what do you add? You add the probability mass function of x, right? Now we have x conditioned on y. So instead of f of x, you have to use the conditional probability mass function of x given y. So again, you add from a to b over x from a to b. What do you add? You add the probability mass function of x given y equals y, which is this. Is that clear? Okay, let us apply this to an example. So now example 5, it says with reference to example 4, okay? And don't worry, example 4, which I gave you last time. And I am writing it here. You don't have to go back. This is the distribution in example 4, okay? What do we want? A, we want to get the conditional probability mass function of x given y equals -1. And in B, we want the conditional probability mass function of y given x equals 1. And C, we want to calculate this probability that y greater than or equal -1 but less than 1 given that x is fixed at 1. Okay. Now we try to answer E. We want the conditional probability mass function of x given y equals -1. So let us write the definition of the conditional probability mass function, okay? Which is this, f of x given y equals what? The joint divided by the marginal of y, okay? Okay, but now here we are fixing y to be what? -1. So let us replace this y by -1. So that means you want f of x given -1 equals f of x and replace y with -1 divided by fy -1. Okay, so all what we've done is we replaced y with what? -1, because this is what's given here. Okay, now here as you see we have the joint of x and y in the form of a table. So we know what are the values of y, what are the values of x, what are the corresponding probabilities. So that means when you get the distribution here, you have to get it for each value of x. What are the possible values of x? -1 and what? And 1. So now here, one time we replace x with -1 and another time we replace it with what? With 1. Now, if we take x -1, so that means you want f of -1 given -1, okay? This -1 is for x. This -1 is for what? For y. Substitute here. So replace x with -1. So you get f of -1, -1 divided by fy -1. This term here, f of -1, -1, is what you get from the joint. This is the joint probability mass function. So if x is -1 and y is -1, then the probability mass function is what? Is 1 over 8. Okay, so it is 1 over 8, this one. Now we want fy at -1. Fy -1, this is the marginal probability mass function of y evaluated at -1. From last time, what is the marginal of y? If you remember, we said the marginal of y, the distribution, marginal distribution of y. These are the values of y, and these are the corresponding probabilities. Okay. So now what's fy at -1? This is -1. So what's the probability, or what's the value of the probability mass function? It is this value, 5 over 8. Here it is, 5 over 8. Now if you divide 8 divided by 1 over 5, 8, you will get 1/5. Okay, so this is the probability mass function, conditional probability mass function of -1 given y equals -1. Now we move to the second value of x, as we said, which is what? 1. So this will give you f of 1 given -1. Substitute here. So replace x with 1. What do we get? F of 1 and the -1 divided by fy at -1. What's the joint probability mass function at 1 and the -1? x1 and y -1. So that means this value, which is what? 1/2, right? So it is 1/2. And then we divide it by fy at -1. Again, fy -1 is the marginal probability mass function of y evaluated at -1. We already obtained it here, which is what? 5/8. Again, this value. This value is the probability that y equals what? -1, no matter what's the value of x. Okay? So now we know the values of x, -1, 1. We know the corresponding conditional probability, I can say, or the values of the conditional probability mass function. We can arrange these results in the form of a table. So we say the conditional probability mass function of x given y equals -1 is, we form the table. Here we take the values of x, and down here we take the values of the conditional probability mass function of x given -1. What are the values of x? -1 and 1. -1 and 1. What are the corresponding function values? These values. 1/5 and 4/5. And they add up to what? To 1. Okay? Now, in B, we want the conditional probability mass function of y given x equals 1. Okay? So again, you can write the definition and then you try to make the details like this. But if you see, as I said, this conditional distribution or conditional probability mass function is what? From the joint, the first table and what? The first row and the last row. Okay, so the values of y are what? -1, 0, 1. -1, 0, 1. What are the corresponding probability mass functions? These values. 5/8, 1/4, 1/8. These. Okay, I'm sorry, folks. Okay. The first row and the last row will give you the marginal of y. This is what I was talking about here to calculate this, right? But the conditional now, this conditional is what? The values of x are what? -1, 1, which are these, right? And what are the values of the conditional? 1/5 and 4/5. How do you get them? Can you see? We divided this by this and this by this. Okay. So now here, to get the conditional for y given x, I want you to show that this is the conditional probability mass function. But let me tell you how do you get it quickly. Now we need the values of y. What are the values of y? These, right? -1, 0, 1. -1, 0, 1. Now we need to calculate the probabilities or conditional probabilities, this or the values of the summation over y. Y from where to where? Function from -1 to 0. Y is x at what? Okay, 1. And what do you add? Fix x at 1, then this is 1. And these are function of the y probabilities given. So all you need is to divide. Okay. So what does it mean? Now replace y. Okay. If you take y divide this by this, so this will be what? F of -1 given this. You will get f of -1. But I want you to work the details like given x. Okay. and then take y equals 0. Now we move so that means you want the third part of our given x. We need this 0 given where is it? This and this what you will get from what? Which is from the previous that y greater than or equal -1. I hope that this is given that x equals 1. So now if we summarize before we start the CDF rule. So far from last time we've talked about probability mass function of what mass function here marginal which conditional probability the conditional probability mass function probability mass given x, okay, right? Y which means given x, we can either talk about the joint behavior of x and the x is fixed at what, or the marginal behavior of x alone, or for y. So this is the distribution you are going to behavior of one of the variables. Now you fix the other at some given than or equal -1 but less than. Now we move to the joint CDF. So if you use this, that means you are going to at the beginning last time we defined the conditional probability mass function, the joint over what for any two random variables. Why? Whether they are discrete or from what to what continuous. What was the definition? It is from -1, this line. But 1 is not included. That capital F and be careful, this equals what? Probability. So less than 1 it means what? X. Less than 1 y means what? Than or equal to stop at 0. And this is for that x between negative probability that y and y from minus -1 and less than, which means so now the x, y, the following. Okay. So this line is the common definition for continuous and discrete. It works for both. But now since we said they are discrete, how do you calculate such type of probability? You use the summation. What do you sum? You sum the joint probability mass function, right? This is the probability mass function, little f, okay? And you add over this region. X less than or equal x. Now I call them S and T. Dummy variables S and T, where S has to be less than or equal X and the T X less than or equal what? T. Okay? Okay. Now if we take example, and we are going to stick to our example, which is example 4 of last time. Okay? And you don't have to go back. Again, I am writing the joint probability mass function for example 4. Now, from this f of x, little f of xy, which means the joint probability mass function, we want to get what? Capital F of x and y. If you remember, when we were talking about the CDF for the univariate case, remember that we said for the univariate case, you have to get it on the real line, and usually we divide the real line, okay, according to the values you have in the domain. Now here the values, for example for y are what? -1, 0 and 1. Now put those on the real line. If you put those on the real line and you divide this into the corresponding intervals, you want to get the CDF on each one. The first one, if you remember, always we take the first interval to be smaller than the minimum. So you take y less than -1, right? And then the second interval, -1 to what? 0. So you say y greater than or equal -1, but less than 0, which is this one. Right? This one. And then you take the interval between what? 0 and 1. Okay? So y greater than or equal 0 but less than 1, which is this one. What's the last one? Usually we say y greater than or equal 1. Y greater than or equal 1. Do you remember this? We do the same for the x. Okay? X assumes only these two values. So now you take the interval before the minimum. So x is smaller than -1. And then you take if x greater than or equal -1 but less than what? 1, which is this. And then you take the interval greater than or equal 1, which is this. So that means you covered the whole two-dimensional space. Okay. Now we need to calculate the probabilities here. Okay. Now, if y is less than the minimum here, right? Y is smaller than -1. Do you have? We don't have, right? We don't have any value smaller than -1. So the probability will be what? 0. Whether x is less than -1 or x is here or x is here. So that means all this is 0. And in fact, if you go back to the properties we mentioned last time for the CDF, remember one of the properties was if negative infinity and y is what? 0. Or f of y and the negative infinity is 0. F negative infinity and negative infinity is 0. By negative infinity, we mean if one of them tends to be what? 2 minus infinity, which means smaller than the minimum value in its domain, which is the case here. If y is less than -1, so that means all this is 0. Y less than -1 and x less than -1, this corresponds to f of negative infinity and the negative infinity. The same here for this line. Can you see all this corresponds to what? X less than -1, which means x goes to minus infinity. So that will be 0. Now, how do we get these? The values here in each cell. I gave you example. How do you calculate it? So if we take fxy at 1 and the -1. Okay, x1. Where is x1? X1 is here. Right? Or here, right? Okay. Because, okay, let me write the definition. F, capital F at 1 and the -1. By definition, it is what? The probability that x less than or equal 1 and y less than or equal -1. Okay. X less than or equal 1. Okay. What does it mean? What are the values less than 1 for x? -1 and 1, right? Less than or equal 1. It means 1 or -1. Okay. Y less than or equal -1. Y less than or equal -1. You have only one value, which is what? -1. So that means you want to get the joint of -1 and the -1 and the joint of 1 and the -1. So that's what I'm writing here. So it is here, there is the f missing here. So please write it. Little f here and little f here. So I mean little f of -1 and the -1 plus little f at 1 and the -1. Little f of -1 and the -1, you obtained it from here, right? -1 and the -1. So what's the probability? This value, 1/8. 1/8. And now you want f, little f at 1 and the -1. 1 and the -1. Now another example says this value 1/2. The marginal
add
CDF
1/2
to 1/8,
the
what we get?
CDF
5y from the previous example. Try to get the rest of the probabilities to be sure, that you understand from last time. The definition was, if I want, okay, recall that's the marginal CDF of x, and I mean recall from the previous lecture, lecture 12. Capital F of x is capital Fx and infinity. And I verified why this last time. Okay, now here, since we are talking about a table discrete case, that means this x takes only two values, -1 and 1. So we have to get capital Fx at -1 and capital F of x at 1. Okay, capital F of x at -1 is what? For using this definition, it will be f of -1 and infinity. Fxy -1 and infinity. So that means you get the marginal of x from what? From the joint. But you let y equals what? negative or goes to what? Goes to infinity. Okay. But as I told you, infinity with respect to our example, this example, it means y is 1, the maximum. The maximum value is 1. So that means you want to get f of -1 and 1. Okay. Now, what's the definition of capital F? Capital F of x, y. It is the probability. Remember the probability that capital X takes values less than or equal what? -1. And capital Y takes values less than or equal what? 1. Y less than or equal 1. Okay. So X is less than or equal -1. What are the values of X? -1 and 1. So that means you have only one value for X. Y less than or equal 1. What are the possible values of Y? Do you remember? Y takes -1, 0, and 1. So Y less than or equal 1, it means Y is -1, Y is 0, Y is 1. So take all these combinations here. And this is a joint probability, which means joint probability mass function. So that means you will get f of x, y of -1 and -1, and -1 and 0, and -1 and 1. Okay, you agree with that? Because y takes values what? Y takes -1, 0, and 1. But x is what? -1, -1, -1. Only one value. Okay. Now from the previous table in the previous slides, you will see that f of -1 is 1 over 8, f of -1 and 0 is 0, and f of -1, 1 is 1 over 8. When you add this, you will get 1/4. I hope that this is clear. Now we need to get capital F of x at what? At 1. So this will be, by this definition, capital Fx at 1 will be the joint CDF evaluated at what? 1 and infinity, right? But infinity in our case is what? The maximum value, which is 1. So it is capital F 1, 1. Okay. Now, what's the definition of capital F? It is the probability that x less than or equal 1 and y less than or equal 1. How do you calculate this probability? Well, from a previous slide, it is the summation, double sum, over x less than or equal 1 and y less than or equal 1. Okay, this. What? You add what? We add the joint probability mass function, little f, of fx, y. Okay? Now, x less than or equal 1, it means what? X less than or equal 1. It means a -1 and 1. Y less than or equal 1, what does it mean? -1, 0, and 1. Remember the values? Okay. Now take every combination and add them. So that means you are adding all the values, 1 over 8 plus 0 plus 1 over 8 plus half plus 1/4 plus 0. Well, the sum is 1, but it's not clear here. So please write it 1 here. Okay? So equals 1. Now we put the CDF in the form of a table. So we need x and we need capital F of x. Okay? Again, we write, we write or we divide the real line according to the values of x. Remember again, what are the values of x? -1 and 1. So that means the first interval, x less than -1. The second will be greater than or equal -1 and less than 1. The following one, x greater than or equal 1. X less than -1 is what? 0. Remember that? Because there is no any possible value below -1. So this probability is 0. And also this one, you know, when you talk about values greater than the maximum, what do we get for the CDF? 1. So that means what you need to calculate is this. Now, x greater than or equal -1 and less than 1, this is capital F at -1, which we get it to be what? 1/4. So this is 1/4. Okay? If you look at this table and the joint probability mass, the joint CDF in the previous slide, you will see that these two lines are the first column and the last column. Okay, so this is the first column, values of x, and this is the last column. Okay, now we have a question says, what's the marginal CDF of y? If you work all the details now from what we concluded here, it will be the first row and the last row in the previous table of the joint table. Okay, so here I said the answer is last row of table, and of course the first row. So far we've talked about what? If we summarize, we've talked about the joint CDF and the marginal CDF. So now we move to what? Conditional CDF. So now the definition says what? The definition says let x and y be jointly discrete. Okay. The conditional CDF of x given y equals little y is given by, this is the notation, capital F of x given y. Okay, for x given y. The definition says that the CDF is a probability, right? Is a probability of this type, x less than or equal x, but you have to keep with the condition. So given that y equals y, this condition. Okay, how do you calculate probabilities? As we said many times, you have to sum over this region. Okay, you add what? The conditional probability mass function. Okay, which we call it what? F of x given y. So that's by definition. So that means to get the conditional CDF, you need first what? The conditional probability mass function. Okay, now we say with reference to example 4, find capital F y given x, where y is fixed at, where x is fixed at 1. Okay, so as I said, in order to get the conditional CDF, what do you need? You need the conditional probability mass function. So that means here you need the conditional probability mass function of y given 1. In fact, we obtained this minutes ago. You will find it in a previous slide. Okay. So if you look at a previous slide, specifically for example 5, you will see that f of y given x is 2/3 if y is -1 and 1/3 if y is 0 and 0 if y equals 1. Okay, it was in fact written in the form of a table. Okay, and these are the values of y, and these are the corresponding values for the conditional probability mass function. Okay, now this looks like the univariate case. How do you get CDF for such distribution? First, you divide the real line according to these values, right? So you take y less than what? -1. This is the first interval. And then you take y between -1 and 0. Specifically, y greater than or equal -1 and less than 0, which is this one. Right? So y between -1 and 0. And then the last one, in fact, it has to be from 0 to 1. right? But can you see the contribution of 1 is 0? In fact, I can eliminate this row because you have no probability, you have no contribution, and you stop with what? These two of x. So that's why the last one, y greater than or equal 0. Okay, now you need to get the cumulative probability corresponding to each of these intervals. If y is less than -1, what is the probability mass function? 0. You don't have any value below -1, right? You start at -1. So that means the first is 0. Okay. The second, between -1 and 0, y greater than or equal -1 and less than 0. Okay. What is the probability at -1? It is 2/3, right? So that means this is 2/3. Now, for greater than or equal 0, okay, that means you add these probabilities, 2/3 plus 1/3. So what do you get? 1. And this agrees with the CDF. Do you remember? Always, if you are below the minimum, the CDF is what? 0. And if you are at the maximum and above, you get 1. In between, you calculate that. Is that clear? Okay, so that's it about today's lecture. Let me summarize to you what did we talk about so far. We've talked about the conditional probability mass function, okay, little f of x given y, or little f y given x. I mean this type, this function, right? Okay. And then we moved to the joint CDF, and we said the definition is an extension for the univariate. Probability that x equals x and probability that x equals x and y equals little y. But you have to get this over the whole xy plane, which means x from -infinity to infinity and y from -infinity to infinity. Okay? And then we've talked about the marginal CDF. And the marginal CDF, how do you get it? You just let the other variable goes to infinity. For example, if you want the marginal CDF of x, what do? In the joint CDF, you let y goes to 0. If you want the marginal CDF of y from the joint CDF of x and y, you keep x from what? From what am I saying? I want to say that if you want the marginal CDF for one of the variables, you let the other goes to infinity. So if you want capital F of x from capital Fx and y, you let y goes to 0. If you want capital F of y, you let x goes to 0. And finally, we've talked about the conditional CDF. So what is the conditional CDF? The conditional CDF, which we denoted by capital F of x given y, it's just also a probability that x less than or equal to x, but conditioned on y equals y. Okay. Now, how do you calculate this probability for the discrete? You just use summation.